Good afternoon to you all. Evan Stamon here for Umughloko, Making a Difference. Today we are looking at the first part of a new topic called calculus. Many of you guys will have heard about it by now. It is one of the key topics from the algebra paper 1 of your examination. And like so many pieces of mathematics, it is by reputation, it is probably more feared than it needs to be. So today we're going to look at an introduction video and look at a topic called a limit. So the first thing I'd like to introduce you to is a piece of notation that looks as follows. Now, what this piece of notation says is the limit, LIM is the abbreviation for what we call a limit. And so what we would say is the limit as x, now you see there's an arrow, tends to 3 of 3x plus 1. And the key thing I'd like to emphasize with you is the tends to, this arrow that's over here. It is not saying that x equals 3. Okay, it does not go x equals 3. Instead, it says x tends to 3. So it's a little technicality, but the one thing it is definitely saying is that x is not necessarily 3. It is getting closer to 3. It is tending towards. You can see the arrowhead points towards 3. So it is heading towards 3 without necessarily becoming 3. And so what it allows us to do is to look at what will happen if we get to values very, very, very close to 3. 2.999, 2.99999, 2.99, or 3.00001, things like that. Values that are very, very close to 3 without actually getting to 3. Now, let's have a look, for example, what would happen if I made x equal to, so let's have a look at this thing. Okay, having looked at that, let's quickly erase this. And let's look at what happens if we look at this in a table. So let's throw this into a table. Okay, so let's draw in a bit of a table here and see what happens, etc. Okay, cool. We don't need to go with too much. We can have a look at just one or two more values and see what happens. Now, what I'm going to do is I'm going to let x equal to 2, let's look at x equal to 2.99. So what's going to happen is we're going to say, cool, this is equal to 3 times 2.99 plus 1. How is this different to anything else you've done up to now? Not much at all. And that's one of the points I'd like to make here. It's got a reputation without necessarily needing to be quite so scary. So what we're going to get here is 8,97 plus 1, which equals 9,97. If we made it equal to 2.999, we're going to get 3 times 2.999 plus 1. All we are doing is substituting, and we're going to get 9.997. If we let it equal to 3,01, it would equal to 3 times 3.01. In fact, I'm going to have a look at here quickly at something. Equals ... 10.0. Sorry, I left off the plus 1. Equals 10.03. Okay, and if you let it equal to 3.001, we'd get an answer of 3 times 3.001 plus 1 equals 10.003. Now, what you'll notice is that these values are pretty close to 10. And so you might have a feeling that if I was to make x equal to 3, all I would need to do is say 3 times 3 plus 1 equals 10. And nothing would be, and there would be no problem. And in fact, limits obey that sort of concept exactly as you've just said. If there is no problem, simply substitute. Okay, so I haven't yet defined for you very well what I mean by a problem, and we'll look at that now. Okay, but as a general rule, with a limit, if there is no problem, all we need to do is treat it as normal and simply move ahead by substitution. So if there is no problem, all we do is substitute. Now, what I mean by a problem, let's have a look at the following one. Let's have a look at the limit as x tends to 3 of x squared minus 9 over x minus 3. Now, what you may notice is that this thing is defined. Okay, this thing is defined. So x squared minus 9 over x minus 3 is defined for all x values that are real except one. X may not equal 3. Now, this is kind of cool because I've not said that x equals 3. I've said that x tends towards 3. X is going to get very close to 3 without ever being 3. Now, what you may notice here is that this is a case, a type of limit where the denominator is causing a value that will be undefined. And so the limit allows us to try avoid this problem by not making it the undefined value, but by making it a value that is so close to that undefined value that we can now perhaps make a judgment call. So if I was to now go and look at what happens here, I could see that this thing would be the same as saying it's the limit as x tends to 3 of x minus 3, x plus 3 over the x minus 3. And so for the moment, I'm ignoring the limit. And please notice where the limit is placed on the right-hand side of the equal sign. And for the moment, I'm ignoring it. And the reason I'm ignoring it because is at this point in time, because of the denominator, x may still not equal 3. Okay? So what I'm now going to do, I've factorized it, and the reason I factorize it is because I know that the denominator and this one factor up top will cancel out. So this is now the limit as x tends to 3 of x plus 3. The rest of the problem is cancelled out. What has happened now is that my problem has gone away. Okay? I no longer need that restriction of x may not equal 3 because I no longer have a denominator that contains a variable. So my problem has gone away, which means I now have no problem. And as we saw on the previous slide, if you have no problem, all I need to do is to substitute. So this is 3 plus 3, which equals 6. Now, what I want you to notice is that I operated in two stages. In stage 1, I had a problem. Okay, there was a problem. In this case, the problem was that we had a denominator, and if we had an undefined value, and so the problem that we had here was we dealt with it. Okay, the problem that we had was the denominator, so we dealt with the problem by factorizing and canceling. The second stage, while having resolved the problem, so to speak, okay, we no longer have a problem. And since we no longer have a problem, we can substitute. And so limit is a thing that allows us to approximate a value or to approach a value without saying it is that value. And so at one stage, we're saying it isn't that value. In the red part of the sum, we're saying it is not that value. And yet in the black part of the sum here, the lower part of the sum, we're saying, well, actually, now that we've sorted out that it's not that value, we're going to make it that value because there's no problem anymore. Now, I want to have a look at this as a function. Okay, let's have a look at this as a graph. If I asked you to graph f of x equaled x squared minus 9 over x minus 3, as a graph, what you would get is a function that looks as follows. Okay, your function would do the following. Okay, would do something along those lines and would look a lot like the function of x plus 3. And interestingly, this graph looks very similar to the graph of y equals x plus 3. Except if you were to zoom in on 3, the value at 3, you would notice that there would be a very small opening in the line. The line would have a very small gap in it. And I know you'd have to zoom in. I mean, I know this is a hand drawing, but if you zoomed in, there'd be a very small hole in the graph. And the question which we're really asking is, what is the value of what is the y value at that undefined point? Now, you'll notice that for every other value except for x equals 3, okay? That for every other value, if I was to say y equals x plus 3, except for the fact that x may not equal 3, that would be good enough to define this function, okay? But I don't want to have that right-hand piece then. I would like to know what's going on as we look as we try to solve this problem of what is in that, what would that hole's value need to be? What value would we need to go in here to remove that hole such that this now is a continuous function, that this function is now one solid continuous line. Now I can't really turn this. I can't really do that in any other way than to say, well, hold on. As I approached this thing from the left-hand side. So what happens as I approach this from the left-hand side? As I did so, this value was increasing. What then happened as I approached it from the right-hand side? This function was decreasing as we approached from the right-hand side. And they were heading towards the same value, and that's the good news. Okay? So if I look at this function and I look at this thing and say, cool, what is the limit as x approached 3 from the left-hand side of x squared minus 9 over x minus 3, we would be able to see that this would be the same as looking at, sorry for that, this would be the same as looking at the limit as x tends to 3, again from below, from the left-hand side, of x plus 3, which we've seen is just going to be 6. If I was to repeat this, looking at it from the right-hand side, you would see that I'd factorize and cancel. And since this is no longer a problem, I will substitute in the 3 and get 6. And the key concept is that since these two values are the same, we therefore conclude that the limit as x tends to 3 of x squared minus 9 over x minus 3 is going to be equal to 6. In other words, we can therefore say that f of 3 will be 6. Now, please notice again, sorry, my fault, I just want to quickly fix something with my notation. Okay, sorry, that's fine. So we are saying that as the x value got closer and closer and closer to 3, the y value got closer and closer and closer to 6. So close, in fact, that if I asked you what you think the value should be if x equaled 3, you would eventually say that, yeah, you know what, it is so close to 6 that I'm going to accept that 6 sounds like a good answer. I know that it can't equal 3 because it is undefined, but if it could equal 3, then 6 would be a good answer. Now, we can look at this in a whole range of different ways. Let's have a look at one more. So let's take another one. This one also involves a denominator. So let's evaluate. Okay, we are trying to find the value of the limit as x tends to, let's make it 3, of x cubed minus 27. Sorry, let's make it something different. Let's choose to make this x cubed minus 8. X cubed minus 8 over x minus 2. Let's, after this, maybe look at the idea of what would be the limit as x tends to 2 of x cubed minus 8 over x minus 2. And so again, what I'd like us to look at is this value, does this value here, does this value pose a problem? Well, again, in this sum, what we should be able to see quite quickly is that because of the denominator x minus 2, the denominator being x minus 2, what we realize is that x may not equal 2. So actually what we're realizing here is that in question A, there is no problem. Whereas in part B, because it is x equaling 2, I do have a problem. Now, in terms of this video and the scope of this video, I'm not going to go too much deeper than this. We are saying if there is no problem, our solution is substitute. Simply substitute in the value. If there is a problem, what we're going to do is we're going to remove the problem. We're going to factorize and cancel first. So in the case of A, it is not a problem. So all I'm going to do is to substitute. So therefore, this thing will equal 3 cubed minus 8 over 3 minus 1 equals 27 minus 8 over 2 equals, in this case, I think it's going to be 19 over 2. And I'm sorted. And again, please notice that this is in fact a value, okay, which therefore answers the part of the question. You can actually see it in the question. It says evaluate. So it's telling you that it wants to have a value as an answer. Okay, let's quickly look at the at the B part of the question. Okay, we are saying there is a problem. So what I'd like you to see here is how the notation, the limit fell away. We say we are going to apply the limit, and effectively what that means is we are substituting. Okay, I want you to notice that here, because I'm still factorizing and canceling, my limit and therefore my notation hasn't fallen away yet. So what I have is the limit as x tends to 3, sorry, as x tends to 2, okay, in this case, because we got the problem value, of x minus 2, we are going to factorize the top, which is a difference of 2 cubes, x squared plus 2x plus 4 over x minus 2. Again, I haven't yet applied the limit, so it's going to be the limit as x tends to 2 of x squared plus 2x plus 4. I'm now going to apply the limit. And so what I'd like you to see is how, when I do apply the limit, how this limit notation has gone away. So what I now have is equals 2 squared plus 2 times 2 plus 4, which in this case equals 12. And this is, again, the value of my limit. Okay, it's the value of this expression. And so what I have here is a value as my answer, which again, when I check my work and I see, have I actually answered the question? Yes, in this case, I have answered the question. And so again, for me, the idea of a limit is this key idea that if it is not a problem, if making this value 3 is not a problem, simply substitute it in. If it is a problem, deal with the problem by factorizing. It's not the only method of doing so, but it's probably it's the only method you need for high school. Okay, there are other methods later on after school, but for high school, we're going to factorize and cancel, and that is going to be our means of removing the problem. And again, once we've removed the problem, we can simply substitute to get our value. Thank you so much.